Hello everyone, welcome to the video solution for physics past paper. This is Cambridge physics paper unit 2 May-June 2017. Let's start. Question number 1. State 2 SI base unit other than kilogram, meter and second. So it is a typical question, generally comes in exam asking the base units or base quantities in a different questions. So if you memorize this table, which consists of 7 base units and base quantities, so these types of questions will be quite easy for you. So the first column, which is this one, this is SI base quantities, and this column is their corresponding SI base units, and they are asking write any two units other than kilogram, meter and second. So other than kilogram, meter and second, you can write any of these 4. So you can write ampere, Kelvin, mole or candela. Part B. Determine the SI base unit of resistivity. If you see the resistivity and its formula, so resistivity is defined as rho is equal to R A by L. L is the length. That means from this formula clearly you can say that unit of resistivity is ohm meter, and this is in fact SI derived unit of resistivity, and we need to find SI base unit. Base unit means we need to give or we need to write this unit in terms of these 7, any of these 7. So meter belongs to base unit list, so this meter is fine, we are okay with this, but we need to figure out equivalent unit of ohm. And if you see the formula, this formula can be rewritten as resistance. Resistance is voltage upon current into area upon length, and area is meter square, L is meter, I is current, area, length, so all these are base, all these 3 have base units, but V has no base unit, so I'm just rearranging V into A by I L, and this V is the voltage, and this V can be written as work done per unit charge into A upon I into length. Now it's easy to understand the units. Clearly I can say that work has unit joule, charge has unit coulomb, and area has unit meter square, current has unit ampere, and length is meter. Still we need to replace joule and the coulomb. Joule is Newton meter divided by coulomb is ampere second, as per definition ampere second into meter square over ampere meter. So moreover, this Newton is still does not belongs to the base ones, so we replace this Newton with its equivalent base unit, and Newton is the unit of force, and force is equal to MA. So we can say that this Newton is kg meter second minus 2. This is Newton, and this meter is there. divided by ampere second into meter square over ampere meter. And now finally you can do your maths. It's just algebra, cancellation, multiplication and division, these kinds of thing. And once you simplify, you have your final answer as kg meter cube ampere minus 2 and S minus 3. This is SI base unit of resistivity. You might think that it is a long way to do. Yeah, it looks long, but because I wrote every possible step just to make you understand. Once you have a habit to memorize your formulae and writing your units, so it takes around maybe 30 seconds to figure out the base units, I guess. Part C. A wire of cross-sectional area 1.5 millimeter square and the length 2.5 meter has a resistance of 0.03 ohm. Calculate the resistivity of the material of the wire in nano ohm meter. So we need to find the resistivity in nano ohm meter, and if you recall, your resistivity formula is rho is equal to Ra upon L. You just need to substitute the values because resistance, area and length is given in the question, but here there is one important point. You must be careful about that. The area is given 1.5 this millimeter square, so you need to convert this millimeter square into meter square. So millimeter square should be converted into meter square, then we are going to put the value in the formula because millimeter does not belong to SI unit. So how do we do that? So 1.5 divided by 10 to the power 6. Okay, so 10 to the power 6 because 1 meter is equal to 10 to the power 3 millimeter, and if we have a meter square, then we must have a 10 to the power 3 whole square, so 10 to the power 6. So our area will be 1.5 into 10 to the power minus 6 meter square, and then now you can substitute your value. So your resistance is 0.03 times area is 1.5 into 10 to the power minus 6 divided by your length, and length is 2.5 meter. Once you simplify this, then your resistivity, the final answer will be 18 10 to the power minus 9 ohm meter, and this 10 to the power minus 9 can be written as nano, so you can say that 18 nano ohm meter. Okay, state what is meant by precision. So precision means how close your measured values are, meaning if you are doing some measurement and your values are 2.1, 2.09 and maybe 2.12, so all values are close to 2.1, so that means your measured values are precise. But if you are doing measurement, one value is 2.1 and then 2.6 and then 2.8 and then maybe 1.8, these kinds of reading, so you have a large spread of your data, large variations are there, so this is less precise, and this one is more precise. So precision means how close your measured values are, and it can be determined by the range of the measurement. So that's how you can define your precision. You can rephrase the statement in your own wording. Explain why the precision in the value of resistivity is improved by using a micrometer screw gauge rather than meter rule to measure the diameter of the wire. Of course, if we measure the micrometer screw gauge, we would have a more precise value. The reason is meter rule has a resolution of zero point 0.1 centimeter or 1 millimeter, while the micrometer has a precision of 0.01 millimeter. That means micrometer screw gauge can measure till 0.01 millimeter, so it is more precise. That means we have a less percentage uncertainty if we use micrometer screw gauge. Question number 2, define velocity. Easy definition, rate of change of velocity or displacement per unit time is called velocity. Question number 2, a ball of mass 0.45 kg leaves the edge of a table with a horizontal velocity v as shown in figure 2.1. Okay, so this is the arrangement. We have a height of the table 1.25 meters. Distance of falling ball is 1.5 to the floor. The height of the table is this, distance is 1.5. Air resistance is negligible. Calculate for the ball the horizontal velocity v as it leaves the ball. This is a projectile motion, a typical situation of a projectile, and we need to find horizontal velocity. Remember, for horizontal velocity we have only one option to solve our problem, which is the equation that we use is only equation is s is equal to ut, or sometimes in some case you can say s is equal to vt. It doesn't matter. It's better to say vt because they are saying horizontal velocity is v, because we are ignoring air resistance, so horizontal velocity stays same throughout the motion. So this v stays same throughout the motion when the ball is falling down, and because the horizontal velocity is uniform, so we use equation s equal to vt. We can find v because we have horizontal distance, which is 1.5. We can figure out v, but the problem is we don't have t. So without t we cannot find v. That means we need to first figure out the value of t, time taken by the ball to reach the ground. And for this purpose we are given vertical height. So we use this vertical height to figure out time. And we know that for a projectile, vertical motion is accelerated motion. In a vertical direction, vertical velocity increases. And if vertical height is given, we use equation s is equal to ut plus half at square. This is the second equation of motion. And if you see this, vertically, initially the ball is not moving vertically. We don't have a vertical motion at a start. So initial vertical velocity of the ball is 0. That means this u is 0. So we have equation, simplified form of equation is s is equal to half a t square. In this equation, this s must be vertical height, not the horizontal distance. So this s is 1.25 is equal to half a is acceleration due to gravity, which is 9.81. As the ball is falling down, so we take positive, into t square. Clearly you can see that we can find t from this equation. You just simplify, make t as a subject of this equation, and then you can figure out t would be equal to 0.5048 second, or t is equal to, if you round it off approximately, it is 0.5. okay, so 0.5. okay, second. So whichever you, so this is the time taken by the ball to reach the ground, and this time t 0.5048 can be used in our equation for horizontal motion to figure out v. So now v is equal to distance, horizontal distance upon time taken, and the horizontal distance now we have 1.5 divided by time taken is 0.5048. So 0.5048. So your velocity would be equal to v is equal to 2.97 meter second inverse. This is your horizontal velocity. The velocity just as it hits the floor. So we need to find the velocity. Now if you see the situation, we need to find the velocity and hit the floor. So now if you see the situation, what is happening here, as ball starts falling down, initially we had only horizontal velocity, but as ball starts falling down like here, along with the horizontal velocity v, which is constant, vertical velocity starts increasing. I'm calling this as Vy. This is a vertical component increasing every point. So V stays same, but vertical velocity keep increasing every time until it hits the floor. At that moment, at the time of hitting, it had a horizontal velocity V, but at that moment again some vertical velocity Vy. So we have some resultant velocity v. That's what we need to find. That's what they are asking in the next part. So we have a horizontal velocity we have found here 2.97, and only thing we need to first figure out Vy, which is a vertical component, and then we can use Pythagoras theorem to figure out V. So let's figure out V. We have a height 1.25 and we have a time to fall to the table. So let's see, since V is equal to, because we are talking about vertical motion, V is equal to u plus at. This is first equation of motion. V is the velocity vertical component when the ball hits the floor. So this is Vy equal u, again initial vertical velocity at the start. So we don't have a vertical motion. So this u is 0. Ball is falling down. So a is acceleration due to gravity, positive 9.81. And t is the time, which is we have found in a previous part, which is 0.5048. Now clearly this is Vy, and Vy you can have a 4.95 meter second inverse. This is vertical velocity. Now your final velocity, your magnitude of the velocity will be, I'm just giving a symbol V dash because I cannot say V. V is the initial horizontal velocity. So V dash is your final velocity, that what you need to find. Okay, V dash is equal to Vy square plus V square root, Pythagoras theorem. Now you can substitute the value. So Vy square is 4.95 squared plus V, and V is I guess we found 2.97 squared and root. Once you simplify this, so V dash would be equal to 5.788 or approximately 5.79 or 5.8 meter second inverse. So this is your magnitude of the velocity, 5.79. What about the angle to the horizontal? Remember, the diagram at the time of hitting the floor. So we had horizontal velocity in that direction v. We found vertical component vy, and this is the v dash, which is the resultant velocity, something like this. This is the v dash that we found using Pythagoras theorem. Angle mean, we need to figure out this angle, which is theta. So this theta is equal to, clearly we need to find tangent inverse opposite over hypotenuse in this diagram, and opposite is vertical component, which is 4.95 divided by 2.97, and once you solve for theta, this theta would be equal to around 58.78 degree, or round it off till 59 degree. This is your angle. Next, the kinetic energy, just find the kinetic energy just as it hits the floor. So at the time of hitting of the floor, kinetic energy half mv square. So half mv squared. V squared we have found. This is the v of the ball. It's not the horizontal or the vertical. This is the resultant v that we found here, 5.79, and m is the mass which is given in the question. This is around, I guess, 0.45. So you can say that kinetic energy is half into 0.45 kilogram, and v is 5.79 whole square, and you can figure out kinetic energy as 7.57 joule. This is kinetic energy. Part 4, the loss in a gravitational potential energy as it falls from the table to the floor. So we need to find the loss of gravitational potential energy as it is falling. If you see, you have a table and this is the ground, here's a ball. So at the top, the ball has a gravitational potential energy, which is mgh. As it is falling down, height is decreasing, so potential energy is decreasing. Clearly all the potential energy is decreased when it hits the ground. So loss of gravitational potential energy, I'm just writing in short, loss of gravitational potential energy is equal to mgh. So mass is 0.45 times 9.81 times height, and height is 1.25 meter. And if you solve this, loss in gravitational potential energy will be equal to 5.52 joule. So this is loss of gravitational potential energy. C part, explain why the kinetic energy of the ball in B3 does not equal to the loss of gravitational potential energy in B4. If you recall the kinetic energy that we calculated in B3, when the ball hit the ground, it was 7.57 joule. Clearly it is greater than the loss of gravitational potential energy, and the reason is, before falling, ball was moving on the table. That means the ball already has some initial kinetic energy. So some initial kinetic energy, that's why the kinetic energy, when it hits, it has a greater value than the loss of gravitational potential energy. So the Young modulus of the material of a wire can be determined using the apparatus shown in figure 3.1. Okay, this is the setup. On one end of the wire is clamped at C, and a marker is attached to the wire above a scale S. A force to extend the wire is applied by attaching masses to the other end of the wire. The reading X of the marker on the scale S is determined for different forces F applied to the end of the wire. The variation of the X and F is shown in figure 3.2. Okay, this is the graph. Force against extension X in millimeter, force is in Newton. The length of the wire from C to the marker for F is 3.5 meters. So this is original length. This is our original length when F is 0. This is the length, original length at the start. The diameter of the wire is 0.38 millimeter. Use gradient of the line in figure 3.2 to determine the Young's modulus E of the material of the wire in terapascal. Okay, so how can we use the gradient of the graph to figure out the Young's modulus? Now, if you see the formula for Young modulus, which is E is equal to stress upon strain. That means sigma over E is strain, and stress is force per unit area divided by strain is change in length per unit length. So if you simplify this equation, you have force into length divided by area into delta L. Or if you replace delta L with X, that means extension, which is the reading from the x-axis. They are using X, so you can rewrite this equation as FL. This L is the original length, which is this. This is L, length. Area, A is pi d square by 4 into delta L, and in place of delta L I am writing X. Clearly from this equation, if you see F upon X, this F upon X is in fact gradient of the line, meaning if you multiply gradient with L over pi d square by 4, you can figure out Young's modulus. So that means first we figure out the gradient, and in order to find the gradient, we need to choose two suitable point on the graph. It's our choice. We can choose this point like this, or maybe this point, but this will be a very small triangle. And what do we do when we find the gradient? So we choose as a big triangle as we can. If you see, for me, most suitable point are this one. I'm taking this point, and this point has a coordinate 10.4. This is 10 point, coordinates are 10.4 comma and 35, 35, and this is a point, the second point, and the coordinate of this point would be 4.4 comma 10. Now we have 2 points. We can use gradient as y2 minus y1 divided by x2 minus x1. So if you use this, you have y2 minus y1 is 35 minus 10 divided by x2 minus x1, which is 10.4 minus 4.4. And remember one important thing here. The extension, which is the values of x, are given in millimeter. So milli 10 to the power minus 3. So don't forget to write into 10 to the power minus 3 here. And if you solve this, your gradient would be equal to 4.16 into 10 to the power minus Newton meter inverse. So this is your gradient. Now we can figure out E. So E would be equal to, E is equal to gradient times length upon pi d square upon 4. And you can see that this length is 3.5, pi is 3.14, and the diameter is 0.38 millimeter. So diameter is 0.38 millimeter. So into 10 to the power minus 3, but it is d square, so you make it a square of these, okay, like this, and divided by 4. And gradient you have found 4.16. You plug in all the values, simplify this, so E would be equal to 1.29 into 10 to the power 11. But they are saying that you need to give answer in terapascal. Tera means 10 to the power 12. So you need to make this 10 to the power 11 as 10 to the power 12. So we shift this decimal on the left side, then our answer becomes 0.129 into 10 to the power 12, or 0.12 means 0.129. You can say equal to 0.13. 10 to the power 12 is tera, and of course this is Pascal, so tera Pascal. So 0.13 terapascal is your final answer for Young's modulus of that sample of wire. Part B. The experiment is repeated with a thicker wire of the same material and the length. State how the range of the force F must be changed to obtain the same range of scale readings. Now if you see, you are changing the thickness. Thickness means you are changing the area of the wire. So if you see, formula E is equal to FL over A into X. You need same amount of scale, that means X should be same, length is same, so you need to figure out about the force. What should be the force if area is changed? Now if you rearrange this equation, so you say that F is equal to E A X, this is EAX divided by length. So this E, X and length, we need same scale, mean X is constant, X should not change, EL also not change. So F is proportional to the area. So if you increase the area, so you should increase the required force in order to get same scale of the reading. That means if area is increased or wire is thicker, you need a large amount of force. So force applied should be increased. Question number 4. State Newton's first law of motion. Typical question. Definition of statement of Newton's first law. An object which is at rest always remain at rest, or moving, if object is moving, will keep moving in a straight line with constant horizontal velocity or constant velocity in a straight line unless acted by some external or resultant force. Part B, an object A of mass 100 gram is moving in a straight line with the velocity of 0.6 meters per second inverse. So this is our first object. Fine. And to the right, the object B is mass 200 gram is moving left. Same straight line as object A with the velocity of 0.8 to the left as shown in the figure. Object A and B collide and object A then moves with the velocity of 0.4 meters second inverse to the left. Okay. Calculate the magnitude of the velocity of B after the collision. When you apply the collision situation, because we are dealing with the momentum and momentum is a vector quantity, so before writing any equation we must see the sign convention. So it's generally, what do we do? We take one direction positive, the other one is negative. So for me, I generally take right direction as positive direction and the left direction as negative direction, but you can use vice versa. That means this is my positive velocity and this will be my negative velocity. And after collision, the particle A or object A is also moving left, so its velocity should be negative after collision. And it's all about collision. We know the law of conservation of momentum. And then how can we do that? You just first you write m1 v1, m1 it's better to write, okay, m1 u1 plus m2 u2. This is total momentum before collision equal to total momentum after collision. So m1 v1 plus m2 v2, sum of the total momentum after collision. Now you plug in the value. Momentum of the first particle moving right side, which is 100 times 0.6, 100 times 0.6, and the other particle is moving left, so its momentum should be negative. So I'm replacing this plus sign with the negative. So mass of the object is 200 times velocity, which is 0.8, and this negative sign is here for minus 0.8, equals after momentum after collision momentum of the first object moving left, so it will be 100 times minus 100 times 0.4. I took 0.4 negative velocities as per this condition, and plus 200 times v. V is the velocity, or v2 is the velocity of second object that we need to find. Now clearly you can solve this equation for v2, and if you solve the v2 will get you will get v2 value as minus 0.3 meter second inverse. So the magnitude of the velocity is v2 is equal to 0.3 meter second inverse. This should be your final answer, because in the question they are asking you to find the magnitude. So we have nothing to do with the negative sign, but they might ask the direction of the particle B or object B after collision. So looking at the negative sign, you say that after collision particle B or object B is also moving in a left direction. But in this question you don't need to talk about the direction, or just ignore negative sign. This is your magnitude of the velocity, 0.3 meters second inverse. The collision between A and B is inelastic. Explain how the collision is inelastic and still obey the law of conservation of energy. When we have a collision between the particle, during the collision, kinetic energy changes from moving energy, or the kinetic energy decreases most of the time, and sound energy is produced and heat energy is produced. Therefore, kinetic energy does not conserve during inelastic collision. But when we talk about the total energy, so total energy is the sum of all types of energy. That means we include the sound and the heat energy produced during the collision. That's why the total energy stays same. So law of conservation of energy holds, but kinetic energy changes. Kinetic energy does not conserve in this collision. Thank you very much for this video. See you in the next one. Have a nice time. Bye.